This is the last topic in this chapter, and it has to do with Young's modulus. Elasticity, and then we'll talk about Young's modulus and tensile stress. So, to understand where this comes from, it's similar when you think of when you pull on a spring, it will expand a little bit, but here it's in a much less pronounced manner. So, for instance, if I take let me get a meter stick here. Here's a meter stick. You don't think of it as when I pull on it that it gets longer. And the reason is it doesn't get longer by much. Because this thing called Young's modulus, which is similar to K, the force constant, is extremely large. And I will talk about those values in a moment. So for example here, to try to understand it, let's take a piece of metal, right? A piece of metal. Maybe it has a cross-sectional area A, and it will have an initial length L, right? This is the length. It has a length L. L, all right? That's the length. What I do is, let's fix it here. Just nail it to a wall or something, or hang it to a ceiling. So I'm going to take that same piece of rod, and I'm going to pull it with a force. And what happens is, it will expand a little bit, depending on how much force I apply it. So I'm going to apply a force F, and what happens is, it will expand a little bit by an amount delta L. The delta L that you have, by how much it will expand, is proportional to the force, or the force is proportional to delta L. So the more the force that you apply, the more it will expand by delta L. If I double the force, this will double. So there is a proportionality constant here. I'm going to call it K. Now, K itself, this proportionality constant K, will depend on how long the rod is initially is. So if it's a longer rod, if the rod is 1 meter and I apply a force and it stretches by 1 millimeter, if I make the rod twice as long, it will stretch by 2 meters. So it turns out that K itself is proportional to the length of the rod, meaning it's easier to stretch a longer rod than a shorter rod, and it's inversely proportional to the cross-sectional area of the rod. If you have like a really thick rod, you're not going to expand it by much. But it's like if it's a really thin string and you pull on it, it's easy to stretch it and even break it. So the force here will equal to, instead of this writing just K, I'm going to write that K itself will depend on the length, the initial length of the rod, and it's easier to stretch a longer rod, so it's inversely proportional to the length, but it's harder to stretch this with a larger area. And then there is a constant here, that is the Young's modulus, Y. And so let me divide both sides by the area. So I get the force over area will equal to, why do I have delta K here? Delta L. Delta L. And I have Y, and then delta L over L. And this Y here turns out to be very large, typically. So let me read you a few values. So the Y is called Young's modulus. And by the way, the term here, F over A, is called tensile stress. And then the term delta L over L is called strain. So let me just write it down. Tensile stress and strain. So this is strain. This is called the strain. And this whole thing here is called tensile stress. Just terminology. And then this is Young's modulus. Young's modulus. It's this, Young's modulus. So let me read you a couple of values here. So Young's modulus here for steel, the units, by the way, are newtons per square meter. You can verify them. for Young's modulus. So for steel, it's 20 times 10 to the 10th power. Copper, 11 times 10 to the 10th. Aluminum, 7 times 10 to the 10th. Concrete, 3 times 10 to the 10th. Wood, it's 1 times 10 to the 10th. So it's easier to stretch wood than to stretch steel, because Young's modulus is smaller for wood. Plastic, it's 0.3 times 10 to the 10th. It's easier to stretch plastic. Now, how about fluids? I mean, they don't have a length. So we will talk about, that one is called the bulk modulus. It's called the bulk modulus. And for example, for mercury, it is 3 times 10 to the 10th. And for water, it's 0.2 times 10 to the 0.2 times 10 to the 10th. And I'm going to let us do an example here. And the example is a 2 meter long, 1 millimeter in diameter wire is suspended from a ceiling, and then you hang 4.5 kilograms from the wire, and to stretch the wire by 1 millimeter. And then it says, what is Young's modulus for this? And then it says, can you identify the material? Well, let's calculate Young's modulus first, and then look at the material. So you have a 2 meter long and then 1 meter in diameter. So let's see here. So the example here. Example. So here is the wire. This is the wire. What you do is you come along and you hang 4.5 kilograms on it. And it stretches. So this is the initial length. L is 2 meters. It's stretched by an amount delta L, which is 1 millimeter. 1 millimeter, that's 10 to the minus 3 meters. And we're given the diameter, and we're told that we're hanging a force on it. And what would that force be? It's the weight. It's mg. So you're putting like a, let me draw a block here, a block of mass m. And so the force, therefore, so the block is being pulled by gravity, and it's pulled by the string here. So the block pulls on the string by Newton's third law, and that pull will be the force. The force will be equal to mg. Okay? And so we will say here, you have the force over area will equal to Young's modulus delta L over L. And so let's calculate the strain. Strain is delta L over L. And delta L is 10 to the minus 3 over 2. Over 2. And so that is 5 times 10 to the minus 4. Okay? And notice the strain is dimensionless. Delta L is in meters, and this is, both have dimensions of length, so it cancels. The stress, or tensile stress, would be, you don't have to do it this way, you could just solve for Young's modulus. It would be F times L over A over delta L. But let's just do it in 2 steps. It will be the force over the area. And the force is mg, and the area is pi r squared. Okay? The mass, I believe it said 4.5 kilograms, and gravity, of course, 9.8, divided by pi r squared, pi. And I think they said the diameter was, let me read it again. The diameter was 1 millimeter. So it was a 1 millimeter in diameter. So that's that's 0.5 millimeters, or 5 times 10 to the 4, 5 times 10 to the 4, to the minus 4 meters squared. Okay. And so we get what? For this, we get, we actually have to calculate it. 4.5 times 9.8 over pi over 5 times 10 to the minus 4 squared. It would be a fairly large number. So you get about 5.6 times 10 to the 7. You get 5.6 times 10 to the 7 newtons per square meter, which makes sense. It has to be newtons per square meter, force over area. So y will be this divided by that. That's why I did it this way. So Young's modulus, y, will be the stress over strain. And you get 5.6 times 10 to the 7 divided by strain. How much is it? We said it's 5 times 10 to the minus 4. And we get something times 10 to the 11. So it's 1.1 times 10 to the 11th. 1.1 times 10 to the 11th. And then it's really 11 times 10 to the 10th. Times 10 to the 10th. And we get what? And it's in newtons per square meter. They said, what's the material? Well, we refer to the table. The table gives everything something times 10 to the 10th. And so 11 times 10 to the 10th. In the table here from the book, it's about, I would say, copper. 11 times 10 to the 10th. So it's probably copper. Now, if you stretch it enough, the wire or the material will break. So there is a region where it stretches. So if you apply this, the force is proportional to this. So it will stretch. So you apply a force, it will stretch linearly, and then it becomes non-linear, and then at some point it will break. Breaking point. And every material will have some breaking point. Our book does not give us the list, but we can find the breaking point. This is, by the way, force. This is delta L. So the breaking point of that material, the book does not list it for some reason, but you can find it. If I find it, I will do an example example for you. And the reason you would think of the breaking point is because, for example, let's say you're on a swing, and you want to play, and it's children's swing, and you're an adult, and you're concerned. Maybe the chain, which is made probably of steel, it has a certain thickness. Will it break as you swing? Because when you swing, right, here is the chain. It's connected here, and you're swinging. You're here, mass M. So when you get here, there will be a net force on the chain. There will be the chain is pulling you with a so the net force on you will be mv squared over r. The net force on you will equal to mv squared over r. This is your mass. So the net force on the chain itself will be mv squared over r on the other side, and it might be of concern that it might break. And practically it does not break. The engineers always make materials just by a safety factor of a few safety factors. So let's say the chain breaks if you put, let's say it's designed for children who are up to, let's say, 50 kilograms, then they will design the chain to be strong enough to hold 100 kilograms or maybe 150 kilograms, just to ensure that it does not break. Okay. The final topic here will be the volume, stress, and bulk modulus. So volume, stress, and bulk modulus. So let me erase the board and write it down. So volume, stress, and bulk modulus. How do we understand this? So imagine you take an object and you sink it into a fluid, or you try to press it from all sides to compress it. So let's say you take an object, and then maybe it's a cubic object, right? Maybe it's a cube, and right, it's a cube, and it's inside the fluid or something. It's being pressed from all sides, from this side and from the back and from here. So from everywhere, it's being pressed. And so if this is area A here, then the pressure on it is the force per unit of area. and the volume will shrink. It will shrink and it will change by an amount delta V. So similar to this, we're going to define F over A, force over area, force per unit of area, which is the pressure, will equal to the change in volume over the original volume, right? The change in volume over the original volume. And here, instead of Young's modulus, you have the bulk modulus. And you would have a minus sign because the volume will shrink. It will be negative. Delta V will be negative. Just to ensure everything will be positive, we have B here. That is the bulk modulus. So, bulk modulus. All right. And there are different values. I think I've read them for you earlier. Okay. So you have, we can refer to them. This is called the volume stress. And this is the strain, or volume strain, or bulk strain. Okay, volume stress and then the volume strain. All right, let us take an example here, just to do an example. By the way, I've read them for you. So, for example, steel, if it's long and you're trying to stretch it, you can have Young's modulus to see how much it stretches. But if you're pressing it from all sides, then you can use the bulk modulus to figure out how much it will compress. And so, for example, for steel, bulk modulus is 16 times 10 to the 10th. And so, let's say you have a 1 meter diameter solid steel sphere, and it's lowered to a depth of 10,000 meters deep in the ocean. So, here's the. So, you take a steel, and it's just 1 meter, and it's in a depth here. It's in a depth. This is atmosphere, and it's a depth of H equal to, I think, did they say 1,000? I read it and I forget. 1,000, actually 10,000 meters, about 10 kilometers. And the question is, by how much will the diameter shrink? By how much will the diameter shrink? So this is 10,000 meters. So I need to figure out what the pressure is there. And then once I find the pressure, I know the force per unit of area. That would be the force over area, pressing it from all sides. So you have water just pushing on it from all sides. So it will shrink, it will become smaller. So let's figure out the pressure first. So the pressure at 10,000 meters would be pressure initially here, which is the atmospheric pressure plus rho GH. And so you got, it will be, the pressure would be 1.01 times 10 to the 5th. That's the atmospheric pressure, plus rho. For ocean water, I think it's about 1,050 or so. Let's see. Yeah, let me just use 1,000 for water, so it's easier. So it's 10 to the 3 here for the density. G is 9.8, and here 10,000 is 10 to the 4th power. 10 to the 4th power. And so this is approximately, let me use my calculator here. And so approximately 10 to the 8th. 1.01 times 10 to the 8th pascals. We get about 1.01 times 10 to the 8th pascals of newtons per square meter. So that's the F over A part. F over A part. Now the bulk modulus, B for steel, it's in a table. So in a test or something, you will be given that. So let me just write it for you. So for steel, I think we said it is 16 times 10 to the 10th. So 16 times 10 to the 10th newtons per square meter. Therefore, delta V over V will be this F over A divided by F over A divided by negative B. So negative B. And so we get negative 1.01 times 10 to the 8th divided by B, which is 16 times 10 to the 10th. And we get negative, don't worry about it, it's just, it means the final volume is less than the initial volume. So we get 6.3 times 10 to the negative 4. Negative 6.3 times 10 to the minus 4. And it's dimensionless because volume over volume would have no dimension. So delta V, by how much did it change? Well, it's equal to the original volume times that number. So it would be negative 6.3 times the original volume. 6.3 times 10 to the minus 4 times the original volume. And delta V is the final volume minus the initial volume, which is, this is the initial volume, by the way, I should say. And so this is, so delta V is the final volume minus the initial volume. So it's V final minus the initial volume. That's delta V equals to this number here, negative 6.3 times 10 to the minus 4 times the initial volume. And so V final would equal to V initial minus this. V initial, we will have V initial minus V initial times this number. So let me factor the V initial, so it will be 1 minus 6.3 times 10 to the minus 4. Yeah. And then the final volume will be 4/3 pi r cubed, pi r final cubed, and this one is 4/3 pi r initial cubed. So you will have 4/3 pi r final cubed will equal to 4/3 pi r initial cubed times 1 minus 6.3 times 10 to the minus 4. So the 4/3 and the pi both cancel, and so we need to take the cubic root of both sides. So the final radius will be r initial times 1 minus 6.3 times 10 to the minus 4, the cubic root of that, so to the 1/3 power. So now we can calculate our final. Our initial is 1 meter, so we can calculate our final to be approximately 0.105 millimeters. Okay, 0.105 millimeters. So approximately just a tiny number, 0.105 millimeters. That's really tiny. Our final, right? From a meter, it changed by 0.105 millimeters. That's 1/100th of a 1% change, going at 10,000 meters deep. So basically, it's incompressible. You cannot compress it. Very tiny, the compression. I mean, even if it's not steel, even if it's another material, even if it's water or mercury or whatever, the change will be, even at that depth, maybe by what? This one is 1/100th of a 1%. If it's something else, maybe it will be 1/10th of a 1%, or maybe just by 1% at 10,000 meters. So it's very, very, very tiny. So the assumption that it's incompressible is very reasonable. Okay, so I'll stop here, and in the next time, it will be for end of chapter problems and practice problems from fluids and elasticity. Okay, I'll see you next time.